All right, in this video, we're going to move on to kind of a strange section in your book where we talk about two completely unrelated topics. They're only related in the sense that at this point in the class, you've learned several, I guess, two main advanced methods of integration, right? You're really good with U substitution and maybe also with integration by parts. And those are the two main methods for integration that you're going to learn in this class. But there's several functions for which neither of those two methods will help you figure out the integral. So even though they're not as common, they're not as main methods, there still are some minor ones left behind that we're going to need to kind of pick up. So what your book does is it gets two of the minor ones out of the way at once. So these are just two different methods for dealing with very specific problems when you're trying to figure out an integral that we can't use integration by parts or use substitutions for. So what I'm going to do is I'm going to start with trig powers. And the issue with trig powers is the way you will attack trig powers will depend on whether the power, the exponent you see, is odd or even. So in this video, I'm going to deal with what to do if you see an odd exponent. And then in the next video, I'll deal with what you do with an even exponent. At any rate, without further ado, odd trig powers. What if I asked you to take the integral of sine cubed x dx? And if I asked you this question, I asked you what function when you take the derivative would give you this as the derivative. And you'd stare at it for a little while and you'd be like, I have no idea. And you'd be like, well, what powers do I have? I'm good with U substitution, but I don't really see what I could make U equal to here. Let's see, I guess I could try making U sine of x, and that would give me U cubed here, which would be really nice. But the problem is if U is sine of x, then du is cosine of x. And so there's no cosine of x floating around. So I can't do that substitution because I couldn't change my dx into a du. That's a bummer. What about integration by parts? Yeah, that's not going to work either. And you're not going to be able to get anywhere. Trust me, it's an algebraic nightmare that doesn't get you to the answer using integration by parts. So you're like, all right, quit telling me what I'm not going to do. Why don't you tell me what I am going to do? Well, it'll end up being a U substitution. And you're like, wait a minute. I thought you just told me that a U substitution wasn't going to work because I can't get rid of the dx. If I make my U sine of x, my du needs a cosine of x, and there is no cosine of x here. Well, I can do a little bit of a trick. And the trick involves this thing called the Pythagorean identity that maybe you remember from a trig class. This Pythagorean identity, it says sine squared x plus cosine squared x always just equals 1. It was kind of your favorite identity in Math 112 at our school because it makes things simplify really nicely. How's that going to help you? Well, essentially, what this lets you do is change even powers of sines into cosines and vice versa. What I'm saying is, if sine squared x plus cosine squared x equals 1, then sine squared x must be the same as 1 minus cosine squared x. And you're like, yeah, how does that help me? Well, over here, I have sine cubed x. I could think about that sine cubed x as sine of x times sine squared x. And why that's useful is this sine squared x I can change into 1 minus cosine x. And you're like, okay, I believe that you can do all this stuff, but I don't see how this is getting you any closer to your answer. Well, check this out. When you're in this form, we could think about a U substitution. Now what we can do is make our U cosine of x, and then our du will involve sine of x, but we'll have this extra sine of x that will allow us to do our substitution. So the trick with odd trig powers is what you always want to do is, since you have an odd number of them, you can think about an odd number as one more than an even number. And so I can kind of peel off one of these signs, and that'll leave me with an even number of signs, 2 in this case. And then that even number of signs I can change into cosines using the Pythagorean identity. And if these were cosines to like the 7th power, well, peel off one of those cosines, you have cosine to the 6th power. And then use the Pythagorean identity to change that cosine to the 6th power into sines. I'll show you how in the next example, and you'll be able to do your substitution. I'm talking too much and not writing enough. If you can get to this step, now we can do our U substitution. We're going to let U equal cosine of x in this example because the trig function that's just raised to the 1st power is the one we'll want for our du. So sort of the other one takes the place of the u. If u is cosine of x, then du is negative sine of x dx. In other words, negative 1 du is sine of x dx. And now I can substitute this sine of x and this dx for negative 1 du. And what I'm left with is the negative, for this negative here, of the integral of 1 minus u squared du. Oh, how convenient. This is super easy to integrate, right? This is one of the first things we learned how to integrate. All I'd have to do is take the antiderivative of this 1, which is just my variable u, and then the antiderivative of u squared using my power rule. So I add 1 to the exponent and bring the 1/3 down in front, and what I get is the negative of u minus 1/3 u cubed. Remember, u is just cosine of x, So if I take this negative and distribute it through and change all the u's into cosine of x, I get negative cosine of x plus 1/3 cosine cubed x. Don't forget to tack on your plus c here. I suppose you could argue that I could have put my plus c here, and we can call this our final answer. The nice thing about this method is it'll work anytime you have either sine or cosine raised up to an odd power. So for example, if I had the integral of cosine to the 5th power of x dx, I can do something really similar. You stare at this, you see an odd exponent, and you're really happy. You're like, just take one of those 5 and save that, so leave that as a cosine, and the remaining 4, so cosine to the 4th x, I will change into sines. How are you going to change cosine to the 4th x into sines? Well, cosine to the 4th x is just cosine squared squared, and cosine squared, using my Pythagorean identity, is equal to 1 minus sine squared x. Take this original one and subtract sine squared from both sides. So what I'm saying is if I view this cosine to the 4th x as cosine squared x squared, then this substitution will work out really nicely, and it'll take me here. And at this stage, I can do a u substitution. It's almost the same u substitution I did over there, except now I want this cosine to be saved for my du. So what that means is I'm going to make sine my u. And if u is sine of x, then du is cosine x dx, and all the pieces work out ever so nicely. And I'm left with just the integral of 1 minus u squared squared du. You stare at this, you might be like, wait a minute, do I know how to integrate that? Yeah, you do. You just have to do a little bit of algebra first. If you expand out this binomial, you could say that this is 1 minus 2u squared plus u to the 4th power. And now we can just use our power rule to figure out this antiderivative. U minus 1 more than 2 gives me 3, but I need that 1/3 out in front. 1 more than 4 gives me 5, but I need that 1/5 out in front. Not a bad idea to tack on the plus c and then change our u's into sine of x. As you can see with this example, when this power gets bigger and bigger, it leaves a little bit more algebra at the end, but it's just algebra, it's not calculus, right? The only calculus that you end up doing is remembering that when you see an odd power, you're going to peel off one of those odd power and save it for later, save it for your du, and that'll leave you with an even power, because 1 less than an odd power is always an even power, and even powers work out really nicely with my Pythagorean identity, even if they involve an extra step of algebra like it did here. All right, one more example before we call this video good. Sometimes you'll see a product of 2 different trig functions raised up to powers. So in this case, sine to the 9th power x times cosine cubed x. As long as one or the other is odd, this technique will work. So I'll show you how we don't need them both to be odd, we just need one or the other to be odd. If you're lucky enough to have both of them odd, then look for which one is the smaller of the 2 odd numbers and use that one for the trick that I'm about to describe, because it's easier to do the trick when the power is smaller here. This sine cubed was easier than this cosine to the 5th power, because 3 is less than 5, because having 5 be large meant that when I subtracted 1, 4 was still pretty large, which meant that I had to do this squared squared trick with my Pythagorean identity, which ended up causing more algebra at the end. So same idea here. Well, it'll work either way. You can either save one of the sines for your du or save one of the cosines for your du. You'll see it'll make your life a whole lot easier if you save one of your cosines for the du. Let me demonstrate. You don't necessarily have to write this step, but it might help you see what you're doing. I'm going to leave the sine to the 9th power completely alone, and then these cosines are the ones I'm going to mess with, again, because this power is smaller. And I'll say that cosine cubed x is the same as cosine squared x times cosine. I'll peel off one of these cosines and save that for my du. So this will end up being my du. If I want to use this for my du, that means sines are going to have to be my u's. There's a problem. I still have these floating around, but I can use the Pythagorean identity to change these cosines into sines so that I have only sines and the one cosine that'll be my du. Because this was only 3, this is only 2, which makes the Pythagorean identity substitution step really easy. I just change cosine squared into 1 minus sine squared, and now I can do my u substitution. The substitution in green is identical to the substitution that we did in blue here, because we have to save the cosine, the thing by itself, for the du, so all the other things, which will be the sines, must be my u's. And when I substitute, I'm left with u to the 9th power times 1 minus u squared du. And kind of like up here, when you're like, wait a minute, do I know how to take the antiderivative of that? Yeah, you do. You just have to do a little bit of algebra first. Take this u to the 9th and distribute it through the parentheses. And now it's as simple as just using our power rule. Add 1 to this exponent, but don't forget to put the 1/10 out in front. Add 1 to this exponent, but then don't forget to put the 1/12 out in front. And if you can remember, tack on the plus c. And I guess if you can remember, or maybe I should state it a little bit more strongly than that, don't leave u's in your final answer. Change your u's back into signs, and then you're good. The comment that I want to make here is the fact that this was signed to the 9th as opposed to, I don't know, signed to the 10th. The fact that this was odd didn't matter at all because I never touched these signs going all the way down, right? That just made this u to the 9th. But if this were u to the 10th, fine, it doesn't matter. You would have taken u to the 10th and distributed it through. I didn't need both of the powers to be odd. I just needed one or the other to be odd. And in the case when they are both odd, take the smaller of the two and use that as your du to make your life easier algebraically. In the next video, we'll talk about what do you do if neither of these two are odd? Or if I just start you out with sine to the 4th power of x, how would you possibly tackle that? And it turns out there's a completely different method for tackling it, hence, different video.